Okay, let's start our conversation around the normal distribution. So, just like we had the binomial distribution for the discrete case, we now have the normal distribution for the continuous case. So this is a continuous probability distribution. And in fact, it's going to be the only continuous probability distribution we use in this class. And there's good reason for that. It's probably the most important and widely used continuous distribution out there. So we're going to focus our attention just on this. Um, so let's note some things. The first is that it's bell-shaped in appearance, right? So it's got this kind of bell curve. So you'll refer to it as bell curve or bell-shaped. And it is also symmetric. It's symmetric around the mean. Symmetric around the mean, which of course we call mu. So I'm going to put mu here because it's always symmetric around this value. But because it is symmetric, if you recall from a couple chapters ago, I think it was chapter 3, that if you have a symmetric distribution, then that means the mean is equal to the median, which is very useful. I'm kind of deleting too much here. All right, so we had the mean here. So the mean is equal to the median. The next thing to note is that it has an infinite range. So that just means that x can vary from negative infinity to infinity. So that means if we go all the way out to the left, this technically goes to negative infinity. And if we go all the way out to the right, this technically goes out to positive infinity. And the variance, which we're still going to call sigma squared, is going to represent the spread of the distribution. So the spread, I just mean essentially how wide is this curve? That's what sigma will represent because we can actually have different normal distributions. For example, let's think about like a fatter curve. So one that's still bell-shaped, but it's just kind of fatter. So this blue, we could say that here sigma squared is equal to 5. We might say that the black curve is sigma squared, say, equal to 1. But we could also, let's see, let me do green. We could also have a curve that maybe looked something like this. It could be super narrow and tall. Sorry, my drawing skills are not very good. We could say that sigma squared here was equal to, say, 1/2. So that's dictated by the variance sigma squared. Okay, I'm going to clean some of this up. I can make it look prettier in the official notes, but for this video, I think this will suffice. Okay, so sigma squared represents the spread of the distribution. Okay, so the total area around the curve, or under the curve rather, is going to be equal to 1. So total area under the curve is equal to 1. So let me just write that up here. So total area is equal to 1. Now, because this is symmetric, that area will be split evenly to the left and right of mu. So 50% of the area is to the left or less than mu, and 50% is greater than or to the right of mu. So what does that mean? Let me just draw a dotted line here. So that means 50% is to the left of mu and 50% is to the right of mu. So if the total area is 1, that means the total area to the left of mu is 0.5 and the total area to the right of mu is also 0.5. So what I'm going to say is that x is normally distributed with a mean of mu, variance sigma squared, and standard deviation sigma. So I might say that x is distributed normally with a mean mu and variance sigma squared. That's just shorthand notation for saying that we have a normal distribution with some mean mu here and some spread, right? Some spread from here to here, sigma squared. Okay, but we also will talk about the standard normal distribution. Standard normal distribution is just normal, except it's a little simpler. It's actually the simplest version of the normal distribution. It has a mean of 0, so mu is equal to 0, and it has a standard deviation and variance, actually, of 1. So we're going to call this random variable z. So here I'm going to say z is distributed normal 0, 1. So it's just a simpler version. So let me just draw this real quick. We have a new bell curve. We're just saying it's going to be centered on 0. And that's essentially it. And it's got some standard deviation of 1. So whenever you see a normal distribution plot, it's generally drawing the standard normal distribution. So the reason we're interested in the standard normal is because we can find probabilities with it very easily. So we can transform between x and z. So we actually did this, I think it was back in chapter 3, that if we want to transform our variable x into a z value, we just use the formula z is equal to x, any x value, minus its mean, divided by the standard deviation. If you recall, we were doing this whenever we were trying to find outliers. We calculated the mean and the standard deviation, and we took every value and implemented this formula to get our z-scores. And I think we said that we have outliers if z values are either less than -2 or greater than +2. But then we can always go back and forth. So if we wanted to get back to our x value, so we have a z-score and we want to get back to x, well then we would just use x is equal to z sigma plus mu. So that's just using some basic algebra. If z is equal to x minus mu over sigma, well, I could multiply both sides by sigma, so I have sigma z is equal to x minus mu, and then I could add mu. So then I have sigma z plus mu is equal to x, and that's where this formula comes from. So let's just note a couple things about z-scores. So z is just a standardized value of x, right? X can range from anything. Most of our values might say range from 0 to 100. But then once we implement the z-score transformation on those values, well then our values are going to range mostly between -3 and 3. And so we can think of z values as the number of standard deviations away from the mean for a given observation. So throwing a lot of ideas out here. If this feels kind of unclear, nebulous, and all of that, that's okay. We're going to do some examples in the next video, and I think a lot of these ideas will come into focus and become a little more clear.